down directly what the meaning of a limit is using this definition. So if I say the limit as x approaches -2 of 1 over x is -half. Okay? Does this make sense?
No.
That if x gets close to -2, then this quantity gets close to -half. Right? Means, directly from the definition, so we can extract the meaning of this. Means, given any epsilon greater than 0, okay, there exists the number delta, okay, such that if x is close to -2, then that leads to 1 over x being close to -half. Epsilon close. Okay, that's a direct, that's just writing the definition for this limit. Alright? There's a small detail here that I'd like to talk about, and that is this part of this inequality. Why is it that we want the distance from x to c not to be 0? Yes? Very good. We want to make sure that the distance from x to c is not equal to 0, so that we're talking about x being near c, not equal to c. Remember, the limit, when we're talking about limits, we're talking about x being near c, not equal to c. When it's equal to c, it might be something totally different, right? Right. No, but the limit, it's not about existing. We don't talk about a limit when we say x equals c. Limit means we're talking about near c. So here's a nice picture. Right? When I say x is in here, well, x can't be 1. Because at 1, it's not equal to 3. We know that. But near 1, it's equal. So we want to make sure that the distance from x to 1 is not 0. Okay? But it is small. Alright? So that's about this technicality over here. That's why that part is there. So we would have to put that in here. Such that, x is close to -2, but it's not equal to -2. Okay, and this part basically guarantees that x won't be equal to -2. Okay? Yes?
Will we need to show less than 0 every time, or is it just...
Yeah. Not less than 0, more than 0. Or 0 less than, yeah. Okay. So, we are kind of ready to write some proofs. Okay? Prove that the limit as x approaches 1 of 2x minus 4 is equal to -2. We know that intuitively, but now using the formal definition, we can prove it. What does it mean to prove it? Proof. I start the proof by saying, remember that thing about being as small as you want, as close to the limit as you want? So the words given any positive number need to be there. Okay? Then the next part is, given any positive number, there exists a number delta. Okay? What's the best way of guaranteeing that there is a delta? Finding one, right? Telling the reader that delta equals this. That's the best way to guarantee that enough delta exists, is by producing one. Okay? So that when x is delta away from 1, that is eventually going to lead to what? Implies that it's less than what? Epsilon, right? Okay. Well, it's not going to be that quick, but after several steps, you're going to see that we're going to get epsilon. Okay? That this number will be less than something equal to epsilon. Something like that. Okay? When you read epsilon delta proofs about the values of limits, it kind of seems mysterious, because the proof is written like this: given any epsilon greater than 0, delta equals this, okay, then this implies this. I mean, it's like, most of the time, it's not clear where they got this delta from, okay? Okay, although you write the proof in that order, you can't plan the proof in that order. You have to plan the proof from where you want to end up and work backwards. So the most important part of writing the proof is not the proof itself, but actually planning the proof. And that's what I want to teach you today for writing epsilon delta proofs. Okay? And it requires, as far as math goes, nothing beyond basic algebra, inequalities and absolute values. That's all. Start from where you want. And if I ask you to write epsilon delta proof on an exam or in the homework, I need to see your proof plan. That's important. Okay? This is how we find delta. Okay? Start from where you want to be. You want to make this less than epsilon, right? Let's start there. F of x minus the limit to be less than epsilon. Let's see what it's going to take for that to happen. Okay, well, let's simplify this. 2x minus 4 minus negative 2 is 2x minus 2 less than epsilon. Right? This will happen if and only if this happens. These are equivalent statements. Right? In other words, if this happens, then this happens. If this happens, then this happens. So they're equivalent statements. And I want to somehow relate this to delta. Right? In order to relate this to delta, I need to have an expression that looks like this. Well, it's not very hard to make this look like that, x minus 1. We can just divide by 2. Again, these statements are equivalent. In other words, if this happens, this happens, this happens. If this happens, then this happens and this happens. So it's completely reversible. Yes? That's your goal. Your goal is to find delta, so your goal should be to make sure you get something like x minus whatever less than some quantity. This is your delta. Okay? If x minus 1 is less than this quantity, then this will work. That's what my proof plan provides. It produces the delta I want. And this is my scratch work. So when I write the formal proof, I have to say, given any epsilon greater than 0, I have to find a delta. Well, here it is. delta is epsilon over 2. And now I have to prove to you that if that delta is epsilon over 2, then I have what I want. Notice how delta depends on epsilon, right? Very explicitly. Okay? Alright. If x minus 1 is less than delta, delta being that, but this is how we write it, then that implies, well, let's do some basic algebra. What is this equal to?
F of x plus 2,
2x minus 4 plus 2, right? Just plugging in f of x. Simplify that. 2x minus 4. Oh, minus 2. And that's equal to 2 times x minus 1. So far these are all equal, right? But now, x minus 1 is less than delta, right? That's the premise we're working with. But what's delta? Epsilon over 2. So this quantity is less than epsilon over 2. So now we have less than. 2 is 2. But this is less than epsilon over 2. Okay? Which is equal to epsilon. So if you read this proof, what does it look like? It looks like, given any epsilon, given any epsilon, I found the delta so that when x minus 1 is less than delta, f of x minus L is less than epsilon. And I've done what I needed to do. And this works for any epsilon. Okay? In other words, if I want f of x to be 1 unit away from here, how far does x have to be from 1? If epsilon is equal to 1, what is delta? 1/2. Okay? Okay, what is the meaning of that? That means epsilon, remember, is the distance from the function to the limit, right? Okay, so if I want this quantity to be within 1 unit of this, then x has to be within half a unit of 1. Okay? And I can do that for any epsilon. Does that make sense? Okay. And that completes the proof. So we're going to put a little box and change it that we finished what we need to do. Yes? Right. So this gives us a way to control how far the function is from the limit, right? Function, limit. If I want the difference of this to be less than 1, right, then that makes delta half. Okay? So in other words, if I want the limit to be about 1 unit away from the function, then I have to make sure that x is within half a unit of 1. That's what I'm saying. And that's just for 1 epsilon. This argument guarantees for any epsilon.